We will now discuss LP spaces. The LP spaces, L for Lebesgue, constitute a rich source of examples and counterexamples in functional analysis. They also form an important class of function spaces for the study for various topics in applied mathematics. For instance, to study partial differential equations, we use LP spaces and subspaces of these LP spaces, which are special spaces called Sobolev spaces and so on. So LP spaces are very important both in analysis and functional analysis, and we will study in this chapter some important properties of LP spaces from a functional analytic point of view. Of course, in a course in measure theory, there will be other emphasis, but here we will look at some of the important things. So what is the basic starting point? So we have a measure space. What does this mean? X is a set, non-empty always, though I may not say it. And then S is a sigma algebra of subsets of X. That means X and empty set are in this, and if you have a countable collection of elements here, then the union is also a member of S, so it is closed under countable unions and it is closed under complementation. If A is in S, A complement is also in S. So this is the basic collection on which one defines a measure. So mu is a measure defined on sets of S, sets in S. Okay, so this is a standard measure. So those who are not completely familiar with measure theory, I recommend that you look at the first chapter in the book on functional analysis, TRIM series 52, which I mentioned at the beginning of this course. There's a rapid introduction to measure spaces. At least the important results which we will use are all stated there, though not proved. Okay, so now you take f from x to r, real valued measurable function. So if you know something on measure theory, you know what. So inverse image of sets of the form. So f inverse of minus infinity is alpha are members of S. So for every alpha in R, that is a measurable function. So okay, so f is a real valued measurable function. There are many equivalent forms of this one particular. Okay, so let 1 less than or equal to p less than infinity, and then define. So I am going to very suggestively put the symbol norm fp, that is equal to integral over x mod fx mod f to the power of p d mu power 1 by p. Okay, so we say that f is p integrable if norm fp is finite. Okay, now so if you say p equals 1, we say integrable. If p equals 2, we say square integrable, and so on. So next, let m be positive, and we say that we denote by mod f bigger than m. This is a set. This is a set of all x in x, such that mod of fx is bigger than m. Okay, so then norm f infinity is the smallest m, so infimum of all m, such that the measure of mod f bigger than m. So this is a set and because of the various properties of measurable functions, this will be a measurable. That means you can define its measure. So this is equal to 0. So m is such that it's almost an upper bound. If mod fx is less than or equal to m for almost every point x, except it may be violated on a set of measure 0. Okay, now you take the smallest such m, so you call the infimum. So we say that f is essentially bounded if norm f infinity is less than plus infinity. Okay, so that essentially, why do we say essentially bounded? It may not be, it may take infinite values or it may be unbounded in some places, but that where it is so is essentially is a set of measure 0 and therefore negligible in the sense of measure theory. Okay, so now we have the proposition. So if p equals 1, we said p star equals infinity and vice versa. If p equals infinity, p star equals 1, and if 1 less than p less than infinity, then p star is the conjugate exponent. So 1 by p plus 1 by p star equal to 1. Okay, so now we meet an old friend, proposition. So we have the Helder's inequality. So 1 less than or equal to p less than infinity and p star conjugate exponent. If f is p integrable, g is p star integrable or essentially bounded. Okay, doesn't matter. I have already defined p star, so that I don't have to go ahead and redo it again. Then mod integral over x mod fg d mu is less than or equal to norm fp norm g p star. So this is very similar to the Helder inequality which we did before. Okay, so proof. So if p equals 1, then p star is infinity. Okay, so integral over x mod fg d mu. G can be brought out by its essential supremum, so that is less than or equal to norm g infinity integral mod f d mu, and that's equal to norm g infinity norm f1. So that is completely proved. So now let us assume that 1 is less than p less than infinity. So we can also assume that f and g are non-zero, because even if one of them is 0, then there is nothing to prove in this inequality. So we have that, if you remember the very first lemma which we proved in this course. So mod fx gx is less than or equal to 1 by p mod fx power p plus 1 by p star mod gx to the p star. Okay, so this is the generalized AMGM inequality which we have proved in the very first lecture in this series. Okay, so now you assume that norm fp equals norm g p star equal to 1. Assume. So if you integrate this inequality on both sides, you get integral mod x fg d mu is less than or equal to 1 by p integral mod fx power p, which is 1, plus 1 by p star integral mod g p star, which is also 1, and therefore this is equal to 1. And in the general case, so now in general you take f by norm fp and g by norm g p star and apply the previous apply this inequality, then you will get straight away the Helder inequality. Okay, so when remark Old remark again, if P equals P star equal to 2, then Helder equals the Cauchy-Schwarz inequality. Okay. So the next proposition is Minkowski's inequality. Again, we are going to follow almost what we did earlier. So 1 less than or equal to P less than or equal to infinity, F and G, sorry, yeah, it doesn't matter, P integrable, essentially bounded if P equals infinity, okay, and then F plus G is also P integrable, and norm F plus GP is less than or equal to norm FP plus norm GP. Okay, so this is the triangle inequality which we proved for vectors. So now we are proving it for functions. Okay, so again we can assume, so proof, assume F plus G is not 0, because otherwise the result is trivially true, there's nothing to prove. Okay, now if you take the function t going to mod t power p, then this is convex for 1 less than or equal to p less than infinity. So mod fx plus gx power p is less than or equal to 2 to the power of p minus 1 of mod fx power p plus mod gx power p. So this just comes from the convexity, the midpoint. So if you had by 2, you have power p less than 1/2 of this, so the 2 power p will cross multiply and you will get this. So this is just the definition of convexity of this function and you will get this. So if you integrate both sides, so integrating, we get f plus g is p integrable. If p is equal to infinity, then of course mod fx plus gx is less than or equal to mod fx plus mod gx, and each is essentially bounded, so implies essentially bounded. Okay, so there is nothing to prove. So now if p equals 1 or infinity, so you get norm. So if p equals infinity, you get from this that norm f plus g infinity is trivially less than norm f infinity plus norm g infinity. And if p equals 1, the same thing tells the integral mod f plus g d mu over x is less than or equal to integral mod f d mu over x plus mod g d mu over x, that is norm f plus g1 is less than or equal to norm f1 plus norm g1. So all that is fine. So we now only have to look at the case 1 less than p less than infinity. So we now assume that 1 less than p less than infinity. So we are now going to, just as we did in earlier, we are going to apply Helder inequality. So you write integral over x of mod f plus g power p d mu is less than or equal to integral over x mod f plus g power p minus 1 into mod f plus g, which is less than mod f plus mod g. So I will write into mod f d mu plus integral over x mod f plus g over p minus 1 mod g d mu. So we are now going to apply Helder's inequality to each one of the terms on the right hand side. So what is So let us take integral mod f plus g power p minus 1 mod f. So by Helder's inequality, this will be less than or equal to norm fp into into norm p star of whatever follows. So integral over x mod f plus g to the p minus 1 times p star, okay, power 1 by p star. So mod f, but p minus 1 into p star is pp star minus p star, which is just p. So this is equal to norm fp into norm integral mod f plus g power p whole power 1 by p star. There's a d mu which I have not written. Okay. But that is nothing but norm fp into norm f plus g p whole power p, and I have taken so p by p star. Okay, so you get that norm, the left hand side, f plus g p whole power p is less than or equal to, apply this to each of the terms, I will get norm fp plus norm gp into norm f plus gp p by p star. Okay. So now, since it's not 0, I can divide this here. So now p minus p by p star is p minus 1 by p star, okay, and that is nothing but 1. Okay, 1 minus p, 1 minus 1 by p star is 1 by p, and so that's equal to 1. So if I divide it, so I get norm f plus g p is less than or equal to norm fp plus norm gp, and that's exactly the Helder's inequality. Okay, so now what have we seen? So if you take this norm fp, so that proves Minkowski's inequality. Then it is satisfies all the properties of a norm, except there's only one property which it doesn't follow. Norm fp equal to 0 does not imply norm f equal to 0. Okay, so it only implies norm fp equal to 0 implies f is 0 except possibly on a set of measure 0. That is, we say f equal to 0 almost everywhere. That means except on a set of measure 0, the result is true. So you do not have this, so you do not have a norm of this. So what do we do whenever we have such a difficulty? We quotient things out. So we say that f is equivalent to g if f equal to g almost everywhere. That means f equal to g except on possibly a set of measure 0. So this is certainly reflexive, this is transitive, and symmetric, and therefore you have this an equivalence relation, and it partitions the set of measurable p integrable functions into equivalence classes. And also, if you have that f1 is equivalent to g1, f2 equivalent to g2, and then you have f1 plus g1 is equivalent to f2 plus g2, and alpha f1 is equivalent to alpha g1. Okay, and so, and also if f is equivalent to g, then you also have norm fp equals norm gp. Therefore, you take any equivalence, so take equivalence classes with respect to equality almost everywhere. So this relationship tilde is equality almost everywhere. So with respect to this relation, you take the equivalence classes and you define, so if I take norm f bar p, you define as norm fp for any f belonging to the equivalence class f bar. Okay, so it doesn't matter which representative you take, so all of them will be the same. Then of course it becomes a norm, because if norm p equal to 0, then norm f equal to 0, then of course f is the function 0 almost everywhere, and therefore you take it as it belongs to the 0 equivalence class, and therefore it becomes a norm. Therefore we make the following definition. So XS mu measure space 1 less than equal to p less than equal to infinity. Let me say first less than infinity. So the space of all equivalence classes under the equivalence relation defined by equality almost everywhere of all p integrable functions is a norm linear space with the norm fp, the norm p. How is it defined? In given any equivalence class, then you take any representative and then evaluate the p norm for that. Okay. So this space is denoted LP mu. Okay. Similarly, the space of equivalence classes of essentially bounded functions is a norm linear space with norm infinity and is denoted L infinity of mu. Okay, so these are the spaces. So when we talk, of course, we will not talk really, make a fuss and talk about equivalence classes. We will say a function is in LP. What do we mean? We mean that this function which we are talking of is a representative, is p integrable or is essentially bounded depending on what the value of p is, and it's a representative of an equivalence class in that space. Now, however, we will not, we will just say it's a function, because we are going to work all our computations via representatives only, and it won't matter which representative you are taking, okay, because any two will be equal almost everywhere and they will not make a difference in all our calculations, which are mostly integration, and therefore if it's 0 on the set, except on the set of measure 0, the integral is automatically 0. So